Hey there everyone, we are now going to talk about the induced EMF by a moving conductor. Okay, let's look at this situation here. We have a moving conductor or a conductor that lies within the vicinity of a magnetic field B. The magnetic field is going into the page or into the screen, perpendicular to the screen down. And there is a conductor, as you can see here, and the conductor is moving at a velocity v from the left to the right. Okay, this is a conductor, so this means that it has free charges, and free charges are allowed to move within the conductor wherever they want. All right, so this means that we can use the right hand rule, because if there is charges that are moving, and remember, this is my right here, okay, this is my right. If there are charges, this is the magnetic field. The magnetic field is going where? Down into the page, okay, which is towards the camera, down into the page. And my right is going this way because the velocity of the charges are going this way because we are pushing the conductor this way. So the charges are being pushed with the conductor this way. Magnetic field is down into the page or the screen. Then we will have a force that will push the positive charges up. The positive charges go up and the negative charges are left behind, or vice versa. Now look at this. This is a conductor that has a positive charge here. What does that represent? Look at it. It represents a battery. Look, because the positive charge here and negative charge here, that's what a battery is. That's a positive and that's a negative. And that's how you create an electromotive force. Now as you move the conductor there, this way, the charges will keep feeling that force and they will get separated, and you will create a battery or an induced electromotive force. If the velocity, if you stop moving the magnet, the charges will go back, because you have to have the charges moving within the vicinity of the magnetic field to feel the force of the magnetic field. Then the charges will recombine again if you stop. If you take the magnetic field to be zero, then the whole thing will crash down, nothing will happen, there will be no induced electromotive force. Okay? We also found out that if the length of this guy here, the length of the conductor itself, if it is longer, it was found out that the electromotive force that is induced is bigger. So let's recap here. The electromotive force, I am going to write it as this. E, that's the electromotive force. The electromotive force was found to be proportional with the magnetic field. The electromotive force was also found to be directly proportional to the velocity. If you increase the velocity, you will increase the electromotive force. If the velocity is zero, the electromotive force is zero. And it was also found to be proportional to the length. If you put all of these together, you can get the electromotive force induced by a conductor is equal to LBV, and sometimes it's best to write it down as VBL. So I'm going to write it down in this kind of like form, VBL. If any of these is not in 90 degrees, as you can see, the movement here to the right, the magnetic field is down, and L is also perpendicular to the motion, the length. If any of these is not perpendicular, you have to add sine theta. All right? And this is the general equation. So as a demo example of this nice equation, which is introducing or inducing an electromotive force by moving a conductor, let's have a look at this nice example. In this example, as you can see the figure, there is a conductor, and this conductor is being pushed by an outside agent, whatever that agent is, and it's being pushed to the left at 2 meters per second. The length of that conductor is 1.2 meters, and the magnetic field value that this whole circuit exists in is 0.3 Tesla. As you can see, the magnetic field is coming right up from the screen perpendicular to you. So let's find out what needs to be done. Find the induced EMF. Okay, that's the equation. The induced EMF is equal to VBL, and if we put the plug in the numbers, the velocity is 2, the magnetic field is 0.3, and L is equal to 1.2 meters. And if we calculate these numbers, we are going to find out the answer to be 0.72. And of course, this is electromotive force. Electromotive force is voltage, and voltage is measured by volts. So this would be volts. Okay, so that's the first part. The second part, and before we go to the second part, let's try to guess where the direction of the current in this circuit here. Is it going this way or this way? All right, let's see. We are going to the left here on this screen. So the left is, this is my left, okay? So we are moving the velocity like this to the left. And remember, this is my left, okay? So this is the left. You can try this on your screen, please. So this is on the left. And the magnetic field is coming like this. So it's coming to me, as we said, but we're keeping the thumb pointing to the left, okay? So the force will be up. So here in this section here, it's going to push the current up, okay? So the current will be going this way, not this way. So it's going to go this way, okay? So this is not true here that we did, all right? So this is the direction of the current. Now let's find out what needs to be done next. If the resistor of the light bulb is 80 ohm, find the induced current. So we need to find the induced current. We know from Ohm's law, V is equal to IR. V is the induced electromotive force. So I'm going to write it this way. And I'm going to write this equation in terms of I. So I is equal to the induced electromotive force divided by R. And the induced electromotive force was found to be 0.72 divided by R, and R is given to be 80 ohms. And if we do this calculation, we can find that the current is equal to 0.009 amps or amperes. Okay, so that's for the second part. The third part, let's find the power delivered to the light bulb. We know that the power is equal to V times I, or the electromotive force times I, and the electromotive force is given 2.72, and that is multiplied by I, which is 0.009. That would be a small number, so the power is equal to 6.5 times 10 to minus 3, and the power is measured in watt. And what is the fourth question? The fourth question is how much energy is supplied in 3 minutes? 3 minutes is 3 times 60, and 3 times 60 is equal to 180. So the energy is equal to the power times time. And if we plug those, energy is equal to the power, which is 6.5 times 10 to minus 3 times time, which is 180. And if we do this calculation, we get 1.17 joules. All right. Now let's go to the final problem, and it says you are using your hand to move the conductor. How much work would your hand apply in 3 minutes? Okay, now how do we solve that? We know that the work, the mechanical work that is equal to F times X times cosine theta. Okay, now let's see. The force that you are applying by your hand is probably going to be this direction. Okay, so the force, and so that's the force, and the displacement are going in the same direction. So theta is 0, cosine 0 is 1. So the force your hand is going to apply is that to overcome the magnetic force acting on a conductor. And we learned that before is ILB times X. X is the distance, but X can be written in terms of the velocity because we do have the velocity, and in 3 minutes we do have time. Okay, so we can rewrite this equation. I'm gonna put it here. So W, which is the work, is equal to ILB X times VT, and we have all of these known. I is the current, and we found the current 0.009. So the current is 0.009. The length is given by 1.2. B is the magnetic field, and that is equal to 0.3. The velocity is 2, and the time is 184 seconds. And believe it or not, if you multiply all of these, you will get 1.17 joules. That's the energy your hand puts into the system to move the conductor across this track of a closed circuit. And how much energy you're getting out in the light bulb? 1.17. How much energy you're putting? 1.17. And that confirms to us that energy is conserved. And that's it for this one. Thank you.